There's a question that's haunted physics for over a century. Not because scientists haven't tried to answer it, but because every answer they give seems to make the problem worse. The question is this: what is the observer? In relativity, the observer is a point in spacetime, a passive geometric coordinate. And in quantum mechanics, the observer is something else entirely. It's something active, something that determines the outcome of physical reality the moment it looks. These two descriptions aren't just different, they're fundamentally incompatible, and yet both theories work. Both predict the universe precisely, and both are, as far as we can tell, true. So either one of them is missing something, or we are. Today, we're going to explore a theory that proposes it's the second option. The thing that's missing might not be in the physics. It might be us. It might be in the structure of the observer itself, and what it means to be a subject in a physical world. This is the subjectivity intersection theory, developed by an independent Japanese researcher named Satoru Watanabe and the Subjectivity Intersection Emergence Lab. This is not a mainstream theory, and it has not been peer-reviewed in the traditional sense, and we'll get to all of that shortly. But it does ask a question that I think deserves to be taken seriously, and explored with the same rigor that we would bring to anything else. Before we go any further, though, I want to say something. I know this community. I know some of the people involved in this research, and when you're close to a subject and when you've had conversations with the researchers, especially when you find yourself genuinely excited by the idea, there's a real risk that enthusiasm can bleed into your presentation in ways that are not fair to your audience. I thought about whether to make this video at all for exactly that reason. But I've decided that the right response to proximity is not avoidance, it's transparency. So let's be very straightforward about where I stand in the matter. I find this theory genuinely fascinating, and I think it's asking some important questions. But I also think that it hasn't yet earned the level of certainty that some of its proponents seem to feel, and both of those can be true at the same time. My goal for this video is not to convince you that subjectivity intersection is correct. It is to give you enough understanding of the theory, its foundations and its claims, and its limitations, so that you can think about it clearly yourself. If I do my job well, you should leave this video with more questions than when you arrived. In the philosophy of mind and foundation of physics, more questions usually means you're getting closer to the real problem. Let's actually get started. To understand why anyone would propose a theory like subjectivity intersection, you need to understand the wound that it's trying to heal. And that wound has been around for a long time. It begins, as many things in modern physics do, in the early 20th century, in a period of extraordinary intellectual upheaval. In the 1920s, Niels Bohr and Werner Heisenberg developed what became to be known as the Copenhagen interpretation of quantum mechanics. It was pragmatic, it was powerful, and it was strange. The core idea was this: quantum systems exist in superpositions, multiple possible states simultaneously until they're measured. And at the moment of measurement, the wave function collapses to a single definite outcome. Before measurement, the electron is neither here nor there. But after measurement, it is somewhere. But Copenhagen was deliberately agnostic about what exactly causes collapse, what counts as a measurement, what counts as an observer. Bohr's answer, which, if you've done research with him, is very in character, is don't ask. Use the formalism to make the predictions. The predictions will be correct, and the deeper question belongs to philosophy, and philosophy can keep it. And to his credit, that was a brilliant pragmatic discipline. It allowed physics to move forward productively for decades, and it papered over a crack that's never really closed. Erwin Schrödinger, one of the architects of quantum mechanics, devised his famous thought experiment specifically to expose the absurdity of Copenhagen taken seriously. Place a cat in a box with a quantum-triggered poison mechanism. Until you open the box, until you observe, is the cat alive or dead? If quantum superposition is real, then the cat must be in a superposition of both. And most physicists responded that the cat's a macroscopic object. Quantum superposition doesn't survive at that scale. Decoherence, the leaking of quantum information into the environment, takes over. The classical world emerges. But this answer, while practically useful, doesn't actually resolve the problem. It defers it. It just says that at some scale the quantum becomes classical. But where exactly? What draws that line? In the 1960s, physicist Eugene Wigner sharpened the problem further with a thought experiment of his own. Wigner's friend. Imagine a physicist, Wigner's friend, sealed in a laboratory, performing a quantum measurement. From inside the lab, the friend observes a definite outcome. The wave function has collapsed. But from outside the lab, from Wigner's perspective, the friend and the entire laboratory are still in quantum superposition until Wigner himself opens the door and observes. So which is it? Has the wave function collapsed or not? The answer depends entirely on which observer you ask. There's no longer merely a thought experiment. In recent years, experimental implementations of Wigner's friend scenarios have been conducted using quantum optical systems, and the results are puzzling. Different observers can, in a real operational sense, give incompatible accounts of whether a quantum event has occurred. The observer is not a passive bystander. The observer is load-bearing. In 1957, a young physicist named Hugh Everett III proposed a radical solution. The wave function never collapses. Instead, at every quantum measurement, reality branches. Every possible outcome occurs in a different branch of a vastly proliferating multiverse. This is the many worlds interpretation, and it is mathematically elegant. It eliminates the collapse problem entirely, and it requires an infinite proliferation of unobservable universes, which strikes many people as a steep ontological price for a tidy question. But Everett's mentor, John Archibald Wheeler, took a different path. He stayed with the observer, and he elevated the observer's role beyond almost anything physics had contemplated before. Wheeler coined the term the participatory universe. His idea was that the universe is not a machine that exists independently of observation. It is, in a sense, called into being by observation. Observers are not spectators of pre-existing reality. We are participants in its creation. Wheeler even proposed the concept of a delayed choice experiment, in which an observer's present choice appears to determine what a photon did in the past. The experiment has since been conducted, and it works, and the implications are still being argued about, and they likely will for a long time. Wheeler's most famous phrase, "No phenomenon is a real phenomenon until it is an observed phenomenon." He wasn't just being mystical, he was being precise about what quantum mechanics actually implies. Somewhere between the equations and outcomes, the observer matters. The observer is not an afterthought, it's essential. But physics, for over 100 years, has not told us what an observer actually is. And that is the wound. That's the history. And that is the gap into which Satoru Watanabe steps. So what does Watanabe actually propose? At the heart of the SIEP, the Subjectivity Intersection Emergence Project, is a deceptively simple idea. Subjectivity itself needs to be defined as a structural component of physical theory. Not consciousness, not awareness in some vague sense, but subjectivity. The condition of being an observer needs to be mathematically formalized and placed inside the equations, not assumed outside of them. The motto of SIEL captures the spirit of the project. Where subjectivities intersect, reality emerges. Let's walk through the core components of the framework. Layer 1. absolute subjectivity and subjectivity intersection. We're going to call it SI for brevity. This is the foundational layer. It's what Watanabe calls the condition prior to any observation, and it's the irreducible fact that there is a perspective at all. Before you observe anything, before your eyes open or your instruments can record a measurement, there's a structural condition that makes observation possible. SI is that condition. It's the intersection point. It's the place where a subject could become present to a world. In Hilbert space, which is the mathematical space used to describe quantum states, SI is positioned as a condition that precedes measurement itself. Something that exists structurally before the wave collapses. Watanabe calls this absolute subjectivity projection. That's the trace that subjectivity leaves on physical geometry, even before it fully engages with the world. Philosophically, this resonates with ideas that you probably are already familiar with. Kant's transcendental subject, the conditions that make the experience possible before experience begins. Husserl's phenomenological reduction, the bracketing of the world to reveal the structure of consciousness itself. But Watanabe is not doing philosophy in a traditional sense. He's trying to make this mathematically rigorous, and he's asking if he can write equations that describe SI. Can we detect it empirically? Are there fingerprints to find in physical data? Then we have layer 2, which is the relative subjectivity and subjectivity intersection coherence. Once again, we're going to go SIC for time. The second layer is where the action happens. It's the transition, and it's what Watanabe calls the SI to SIC transition. When absolute subjectivity meets the conditions of the physical world, something crystallizes. The subject becomes coherent with its movement. The observer and the observed lock into a stable relationship, and this is subjectivity intersection coherence, or SIC. Think of it as a phase transition. Water doesn't gradually just become ice. At a precise threshold, something clicks into a new configuration. SIC is that threshold for the observer, the moment of which the structural possibility of perspective becomes an actual, situated, embodied perspective, and in doing so, participates in determining what the world looks like. Watanabe calls this threshold the SIC gate. And this is where the theory makes its most provocative claim. It's not merely that the observer influences reality. That's already implicit in standard quantum mechanics. But that this influence has a definite structure. It has a geometry and a threshold. The transition point that can, in principle, be detected empirically. This is the claim that distinguishes SIEP from purely philosophical accounts of the observer. It's not just proposing a metaphysics, it's proposing a physics, and one with measurable signatures at that. The third layer. The third observer. We're going to call it O3. To me, this is the most philosophically intriguing component of this framework. In the standard quantum mechanical picture, you have two things: the observed system and the observer, subject and object, the watcher and the watched, if you will. It's a standard quantum mechanical picture. And the problem, the observer problem, is the strange unresolved relationship between them. Watanabe proposes that there has to be a third element, what he calls O3, the third observer. O3 is a non-internal observational structure. It's not inside the neural system. It's not inside the quantum measurement apparatus. It exists at the intersection of the two, simultaneously referencing both and uniquely determining the correspondence between them. You might think of it as the frame that makes the picture possible, not the canvas or the paint, but the structural condition that allows both to cohere into meaning together, if that makes sense. It's an unusual claim, and I want to talk about it for a second because I think it's worth taking seriously before we even evaluate whether or not it's correct. The standard picture in both physics and philosophy of mind is binary. There's a world out there, there's a subject in here, And the question is how do they relate? What Watanabe is suggesting is that the binary framing itself is the problem, that the relationship between observer and observed is not a secondary feature of reality, but is itself primary, that the intersection is the thing. This has a resemblance to relational ontologies in philosophy, the idea that relations are more fundamental than the things that they relate. And it has some structural similarity to ideas in quantum information theory, where the information exchange between systems is sometimes treated as more fundamental than the systems themselves. Whether O3 is a genuine physical entity, or some kind of mathematical convenience, or a metaphysical category mistake, those are exactly the kinds of questions rigorous engagement with this theory needs to answer. Here's where the theory becomes genuinely unusual, and I think the most interesting questions arise from. Watanabe hasn't just proposed a philosophical framework. He has attempted to test it empirically. His method involves comparing EEG recordings of human neural activity with the outputs of quantum computers. In some cases, quantum computers located thousands of kilometers away. In one study, participants in Japan had their brain activity measured while quantum measurements were being made in a device in the United States. A distance of approximately 8,800 kilometers. No casual signal can travel between two systems in the time frame of the measurements. The hypothesis is this. If subjectivity has a non-local quantum coherent structure, if SI is a real physical condition, then we should detect statistical correlations between brain activity and quantum measurement outcomes that cannot be explained by any classical causal pathway. His reported results are striking. Across studies involving dozens of participants, he reports statistically significant correlations between EEG signals and quantum measurement outputs, with some Pearson correlation values exceeding 0.6, and that's with false discovery rate correction applied. In his most recent work examining what he calls the intersection-defined phase emergence, he reports detecting a discontinuous phase transition in a relational order variable constructed at the intersection of neural curvature dynamics and quantum measurement geometry. This transition was observed consistently across 26 independent subjects. And in all 26 cases, with a p-value of approximately 3 times 10 to the negative 8th, if those numbers hold up under scrutiny, it would be extraordinary. Not just for SIEP, but for physics and neuroscience more broadly. But that if requires serious examination, and it is a huge if. Before turning to the critique, I want to give us a sense of where SIEP sits in the wider landscape of theories that take the observer seriously. This theory doesn't exist in isolation. It belongs to a tradition of attempts to solve this problem, and comparing it to its neighbors helps clarify what is distinctive about it. I think at this point we're all familiar with most of these ideas, but we're going to just have a brief overview just as a refresher course. Cubism was developed by Christopher Fuchs and Rüdiger Schock, and it proposes that quantum mechanics is not just a theory about the objective world, it's also a theory about the beliefs of its agents. When you assign a quantum state to a system, you are expressing your personal probability assignments about what you will experience when you interact with it. That the wave function is not a feature of reality, it's a feature of you. And that makes cubism obviously deeply subjective. It shares SIEP's insistence that the observer cannot be factored out of the physics, but the two frameworks diverge sharply on realism. Watanabe wants subjectivity in the ontology, as a real structural feature of the world. Cubism places it in epistemology, in the agent's beliefs. For cubism, there is no fact of the matter about quantum state independence of some agent. For SIEP, SI and SIC are the real physical conditions, not just epistemic states. Orchestrated objective reduction, or ORCOR. ORCOR was developed by Roger Penrose and Stuart Hameroff. It proposes that consciousness arises from quantum computations in microtubules inside neurons, and that these computations involve a physically real collapse of the quantum wave function called objective reduction, and it's tied to the geometry of spacetime itself. SIEP and OR both try to connect quantum mechanics and consciousness through brain processes, but they approach it differently. OR locates the connection in a specific physical mechanism, microtubule quantum computation. SIEP is more structural. It's asking about the geometry of the observer relationship itself, rather than the particular neural substrate. It's worth noting that Stuart Hameroff has reportedly expressed interest in Watanabe's work, which is a notable data point, even while we hold appropriate caution about what interest means at this early of a stage. Then we have rational quantum mechanics. Carlo Rovelli's relational interpretation proposes that quantum states are not absolute, but always relative to the observer. There is no view from nowhere. Every description of a quantum system is a description relative to some other system that is interacting with it. This is structurally similar to SIEP in a few important ways. Both reject the idea of an observer-independent quantum state. Both take the relational structure of the observer seriously as something that must be built into the physics. But there are obviously differences. Rovelli's framework doesn't assign special status to conscious observers. Any physical system can serve as a relational frame. Consciousness is not privileged. The specific character of being an experiencing observer is exactly what the theory is trying to formalize. The observer has a structure that matters in its own right. And then Integrated Information Theory, IIT, was developed by Giulio Tonomi. It proposes that the consciousness is identical to integrated information, quantified as phi. Any system with sufficiently integrated information has some degree of consciousness. This is a form of panopsism in which experience is a fundamental feature of certain kinds of physical organization, not an emergent accident. SIEP and IIT are both trying to give consciousness or subjectivity a formal, measurable structure, but IIT starts from phenomenology, from the intrinsic properties of experience, and works outwards to the physics. SIEP starts from the physics, from the observer problem in the quantum mechanics, and it works its way toward the subject. They're approaching the same problem, they're just approaching it from opposite directions. What's notable is that none of the frameworks, Cubism, OR, Relational QM, IIT, or SIEP, have achieved anything close to scientific consensus. The fact that serious thinkers propose such diverse answers to the observer problem is itself evidence that the problem is that deep. The field is genuinely open, and SIEP is a new entry into the conversation, and whether it will prove to be a significant one is still open. I think that this theory deserves honest engagement, rather than either uncritical enthusiasm or reflexive dismissal, and there are genuine reasons to be cautious about SIEP. All of Watanabe's work exists as preprints on ResearchGate, Zenodo, and OSF. None of it, at the time of making this video, has been published in a peer-reviewed journal, and that is important. Now, peer review obviously isn't perfect. An unfathomable amount of important work has been dismissed by journals, and plenty of weak work has been published in them. But the process of independent expert scrutiny, having specialists in quantum physics, neuroscience, and statistics examine the methodology and try to find the holes, is genuinely valuable. Without it, we can't know whether the statistical methods are being applied correctly, or whether the controls are adequate, or whether the results would replicate under independent conditions. We are, for now, in a state of appropriate uncertainty. The EEG quantum correlation experiments also deserve careful scrutiny. Long-distance correlations between brain activity and quantum computers would be extraordinary. Not just for SIEP, but for all of physics. If Watanabe's results are genuine, they represent a challenge to our most fundamental understanding of locality and causality. Legitimate questions that a skeptic would ask: how were the experiments blinded? Could the correlations be artifacts of the data analysis pipeline? Is the p-value threshold adequate given the number of different correlations being tested? How are the confounds like electromagnetic interference, shared timing signals, researcher expectation effects, how are all of those things being controlled? And they're not hostile questions. These are questions that any careful scientist would ask. And there's a deeper conceptual question too. Even if the correlations are real, do they mean what Watanabe says they mean? A correlation between EEG signals and quantum measurement outputs, however striking, does not automatically demonstrate that subjectivity is a non-local quantum phenomenon. That interpretation is doing a lot of work. The theory uses language from quantum mechanics, Hilbert space, coherence, wave function, phase geometry, and in ways that extend well beyond their standard physical meanings. And that's not automatically a problem. Theoretical physics is full of conceptual extensions that seemed like overreach until they became established theory. But it means that we should be careful about letting the mathematical language create an impression of rigor that the underlying concepts may not yet have earned. When SIEP talks about subjectivity in Hilbert phase geometry, we should ask this. Is this a precise mathematical claim that makes specifically testable predictions that differ from alternative theories? Or is it a philosophically suggestive analogy dressed in formal language? That is not a rhetorical dismissal. It is a genuine question the theory needs to answer in order to mature. With all of that being said, dismissal is incorrect in response to this theory. The problem that SIEP is trying to solve is real. The observer problem is not a fringe concern. It is acknowledged by some serious physicists as one of the deepest unresolved issues in the foundations of physics. Carlo Rovelli, Roger Penrose, Christopher Fuchs, serious thinkers, have spent careers grappling with versions of exactly this question. The idea that subjectivity needs to be formally integrated into physical theory is not obviously wrong. And the experimental program, however preliminary, is at least trying to attempt to move the question out of pure philosophy and into empirical theory. That instinct is valuable, even if the methodology needs more scrutiny and the results need independent replication. The appropriate stance is interested skepticism. Take the question seriously, hold the answers lightly, and watch what happens. So let's end the substantive part of this video with a question that I find genuinely important. What would it take for SIEP to be taken seriously by mainstream science? That's not a rhetorical trap, it's a real question. And it's a question that any mature scientific theory should be able to answer. A framework that cannot say what would falsify it is not yet a scientific theory. It is a philosophical program waiting to become one. And here's what I think the honest answer looks like. Independent replication. The EEG quantum correlation results need to be reproduced by researchers with no connections to SIEL, using independently designed protocols. This is non-negotiable in science. Peer review. The papers need to survive rigorous journal submission, and it's not because journals are infallible, but because the process forces structured engagement with criticism. It needs sharper predictions. The theory needs to make specific quantitative predictions that distinguish it from alternative explanations. If SI is a real physical condition, it should produce specific measurable signatures. What are they? Under what conditions would the theory be wrong? Conceptual precision. The relationship between SI, SIC, and standard quantum mechanical formalism needs to be made more rigorous. Where exactly does SIEP diverge from existing quantum theory? What does it predict that relational QM or IIT or cubism would not? These requirements are not unusual. They're what any new theory in physics needs to do. The question is whether ISEP can do them. And I think watching that process unfold, watching the theory either sharpen into something testable or dissolve under scrutiny, is exactly what this community is positioned to do thoughtfully. So where does this leave us? Satoru Watanabe and the Subjectivity Intersection Emergence Lab have proposed something genuinely ambitious. I mean, think about it. A 3-layer observer model. A formalization of subjectivity as a structured element of physical theory. An experimental program designed to test whether the observer leaves a detectable mark on quantum measurement from thousands of kilometers away. We've traced the history of the problem, from Copenhagen through Schrödinger, Wigner, Everett, Wheeler. We've placed the theory in the wider landscape of quantum interpretation and consciousness research, and we've looked honestly at what the theory still needs to demonstrate before it can claim a place in mainstream scientific conversation. Is SIEP right? I don't know. And I think anyone who tells you that they know in either direction is outrunning the evidence. But is it asking the right question? I think it might be. The history of science is, in part, a history of questions that were too inconvenient to ask. The geometric model was convenient. The static universe was convenient. And in each case, the anomaly that didn't fit, the inconvenient observation problem, eventually turned out to be the most important thing to look at. The observer problem is inconvenient. It sits at the junction of physics and philosophy, and it refuses to be neatly assigned to either. It implicates subjectivity, the most intimate thing any of us know, and the structure of physical reality. And for 100 years, mainstream science has found ways to bracket it, defer it, or declare it somebody else's problem. Maybe the answer, when it comes, will dissolve the question entirely. Or maybe the observer, us, maybe we turn out to be load-bearing after all. And I think that that's worth thinking about, carefully, rigorously, and with the humility to hold our conclusions lightly. The primary papers and preprints are all linked in the description, along with companion reading on the observer problem, the hard problem of consciousness, and the landscape of quantum interpretation theories. I strongly encourage you to read them, not to believe them, but to think with them, because that's what this channel is for. Have a good day.